Okay, fundamentally we can represent, and we can think about this as the nth roots of 1. If we take the first complex number, moving it in an anti-clockwise sense away from 1, so around this angle, we get z2, and then from there we would get z3 for z cubed equals 1. Now, let's actually start applying this, but before we apply it, we need to know a couple more things, and then we'll start seeing if we can throw some exam problems or some interesting solutions, or no, interesting problems at it, and see where what we can come to in terms of solutions. Let's also say that Z2 we're going to call omega. And what do we know about Z2? Let's go back to the diagram. Z2, I'm talking about this one. Z1, if we were to utilize it here, we're not going to utilize it here per se, but this one is just 1. So there's no requirement for us. You call it a letter, but there's not so much of a requirement. This one, however, is a little bit more complicated, and we're going to simplify it down to just the letter omega. Now, let us recall what we know about this. Z2 was cos 2/3 pi plus I sine 2/3 pi. So Z2 squared would be the square of this. Now, rather than squaring this, which you could do, you'll end up with a little bit of trigonometry to do to come up with the same output, but you can also square this here. I've had enough of the screen, let's remove some of the screen. You can also square this here. If you square this, you'd have minus a half times minus a half times I root 3 over 2. Then you'd have I root 3 over 2 times minus a half, and I root 3 over 2 times I root 3 over 2. Or you can use whatever method otherwise you use. You could use Pascal's triangle. You will find that what you get is something quite interesting, and I suggest you pause and have a go at that. Don't worry about r squared. The reason why r squared is not in here, I technically could put my r in there and also square it. The reason why r squared is not in there is because remember that it is equal to 1, and 1 squared is 1, so there's no requirement in my opinion, but I've put it there just in case. No, De Moivre's theorem can be used to show the relationship between z and z squared in the terms of arcs. So if you want to, we want to also have something that will aid in the next part of our conversation. You could use De Moivre's theorem here, and therefore you'd put the 2's in here, so we'd have 4 over 3 pi. And another thing, the one I think is actually definitely worth doing, is actually just squaring this and seeing what it looks like. What you will find is that when you square this value, when you square z2, you will have 4/3 pi as the outcome of the angle. In other words, and this is the phrase I've used here in very poor handwriting, it's quite hard to write on this thing in my opinion. And if you square a complex number, you add the arcs together. So you add the 2/3 pi plus the 2/3 pi, you get 4/3 pi. So, which is exactly, this is the main point, this 4/3 pi is exactly the angle for Z3. So that is to say, when you square Z2, which let's not forget what it represents, this, when you square that, if I take this and I decide to square it, so I'm going to take this value, whatever that value is, I will get this. And as I've mentioned, there are ways in which I could prove this. You could square this, and you will find you will get, again, this. You can square, you can square this, but I would suggest you use De Moivre's theorem and plug in the value of 2 in here, and again, you will get the complex number, this. And once more, it is also another way of visualizing, another rule that we can talk about another time, is that if you square a complex number, you add, in these circumstances, if you square this complex number, you add the arcs. So 2/3 pi, arcs being the angles, 2/3 pi plus 2/3 pi, you'll get 4/3 pi, which is z cubed. We can conclude therefore, and again, have a go at it, don't take my word for it, square these, play around with the trigonometry, De Moivre's theorem for this one. This is simply just multiplication I out. Don't forget that I times I is minus 1. You will see that the complex number you produce is this. I've butchered this diagram to make that make sense, or to aid in perhaps making that make sense. The idea is that by squaring Z2, we get Z3. And if Z2 is omega, therefore Z3 is omega squared. This rule here will be advantageous for problem solving later.